This is the RTL Development of Communication Protocols team with Everett Bullock, Zach Duhon, Kevin Robbins, and I'm Jacob Griffin. The point of this video is to give some background information, including our goal and the underlying protocols we utilized, then describe our specific implementation of our pipeline, how we validated it, and then some conclusions and further work that can be done. First, let's start with some background information. To give a brief overview, the goal of this project is to increase the utilization of accelerators by developing an interface that reduces the latency and increases the bandwidth of current PCIe interconnects. To achieve this goal, we aggregate 4 PCIe lanes by first routing individual packets to discrete hardware subunits, then returning the completed results to the originating PCIe lane. The protocol that we're utilizing is PCIe. This is a high-speed communication protocol used for physically close hardware. It uses pairs of data wires and can handle up to 32 gigabytes per second when in its 4.0 by 16 configuration. The data is sent in transaction layer packets, which I will often refer to as TLPs. To develop our software, we used Verilog, which is a hardware description language, and can be used to build up complex logic modules and connect modules together. Our pipeline was constructed of submodules, which were each their own Verilog file. We also had a test bench which wrapped around our pipeline and was able to read in the inputs and was able to read the resulting outputs to test the functionality of our pipeline. We can then synthesize this code and run it on FPGAs. Next, let's talk about our specific pipeline design. To start, each PCIe lane that we have coming in goes into an input link router. This router reads the packets coming in and directs them to the correct hardware subunit buffer. This buffer filters through the different input link routers and selects which router is ready for data, reads in that data, and passes it on to the hardware subunit. The hardware subunit then completes the task defined in the TLP and passes it on to the output link router, which takes in the completion from the hardware subunit and the TLP from the hardware subunit buffer, forms the completion packet, and then passes that to the appropriate PCIe output. It passes it first to the output link buffer, which then passes it on to the PCIe lane. The first submodule in our pipeline is the input link router. This submodule interfaces directly with the test bench and signals it when it is ready to receive data. The test bench then inputs 32 bits at a time. Input link router then looks at this TLP to determine what kind of request it is and routes it to the correct hardware subunit buffer. In our pipeline, there are 2 buffers, one directly after the ILR and one directly after the OLR. Both buffers are designed in the same way. It starts out with a buffer mux, which rotates between the lanes and signals when it is ready to receive data from that lane. If that lane is ready to give it data, it takes in that data and puts it into the buffer memory. That data then progresses through the buffer memory and is output to the next module when it receives the appropriate ready signal. The last distinct module in our pipeline is the output link router. The output link router is broken down into 3 submodules. The first, the ingress, handles the hardware subunit buffer and the hardware subunit. It reads in the TLP from the hardware subunit buffer and, if necessary, reads in any payloads and completion statuses from the hardware subunit. It then takes these together and passes it on to the sorter. The sorter then takes the TLP and translates it into its corresponding completion header and takes in any payload if applicable. It then outputs this completion header and the payload to the egress stage. The egress stage then routes this payload and the completion header back to the appropriate lane that it originated from.
Howdy, my name is Kevin Robbins, and I'm going to go over the validation portion of our project. The validation portion consists of 2 different sections. The first is the TLP generation, and the second is the test bench. TLP generation is a C++ program that randomly generates TLPs and their corresponding completion headers. These TLPs and completion headers are used as expected inputs and outputs in the test bench. The TLPs and completion headers are printed out into 2 separate text files. The first step of TLP generation is to set the type field. The rest of the fields are then set off the type field. So type can be rather 0, 2, 4, or 5 and is randomly selected. Step 2 is to then set the format field according to the table below. Each different type has certain format fields that are allowed. The rest of the remaining TLP fields are based on the type in the format fields. The third step is to generate payload if it's necessary. So if the type field is 0, meaning that it is a memory read or write request, payload is generated. It is generated into 32-bit lines using a hash function. The hash function takes certain bits of the address field of the memory read and write request and negates these specific bits. The number of lines generated for the payload is equal to the length field. Lastly, the generated payload is inserted into a payload vector. The fourth step is to create a completion header for each TLP. This completion header is going to be used as the expected output in the test bench. It will be compared to the actual output from the pipeline. The fields of the completion header can be seen below. The final step is to generate the binary values of all the fields for the TLP and completion headers. These corresponding binary values are then stored inside two separate vectors, one for the TLP and one for the completion header. The TLP, completion header, and payload vectors are all printed to text files. The next step of the validation process is the test bench. The test bench starts by reading in 4 TLP generation input files, one for each PCIe lane. These TLP generation input files are then read into TLP vectors. These 4 vectors are then sent through the pipeline, and their outputs are stored into 4 separate vectors. Next, the test bench reads in 4 TLP generation expected output files. These files contain the completion headers and the corresponding payload for the 4 TLP generation input files. They are stored into expected TLP output vectors. The actual TLP output vectors are then compared to the expected TLP output vectors, and a pass or fail will be returned from the test bench.
And lastly, our conclusion. For results, we were able to generate 4,000 random TLPs, put them through our pipeline, and through our test bench, able to validate that the outputs that we received matched up with the outputs that we expected. This shows that our pipeline can process any TLP that is sent to it. We were also able to create this pipeline using a flexible design which allows for the number of lanes and hardware subunits to be implementation specific. Also, using some timing analysis, we were able to find that it only takes on average 21.052 cycles per 32-bit input to receive an output. This lines up closely with our targeted speed. For future work, we want to implement and verify on an FPGA. We want to also improve on the current design to reduce latency and increase efficiency in any way that we can. We would also want to develop safeguards to protect against faulty TLPs, as it is difficult to detect these and to handle them. We'd also want to expand the design to include C6, the cache coherency interconnect for accelerators. Lastly, we'd like to thank Stavros Kalifatis, Ping Wang, and the Texas A&M ECEN department.